A very good evening to everyone, and I hope I'm audible. And welcome all of you to today's webinar on the topic Introduction to Nano Satellite Design, hosted by the Satellite and IT Division of the SEDS chapter of Sri Lanka Technological Campus, Sri Lanka. My name is Hiruni Pires, and I'm the moderator for this event. Therefore, giving a brief introduction about myself. I'm a second-year undergraduate studying biosystems engineering at the Sri Lanka Technological Campus, and I'm currently affiliated with the Satellite and IT Division of the SEDS chapter of Sri Lanka Technological Campus. Before we move further, I would like to review the functionality of today's webinar. This webinar will be broadcasted simultaneously as a Facebook Live on our social media platforms. Therefore, your active participation is very important throughout the session. Right now, we have everyone on mute to avoid background noises that may distract you from listening to the webinar session. We'll also be hosting a live Q&A session to answer all of your questions. So please make sure to drop in all of your queries or comments onto the Wevox platform or to the chat box throughout the webinar. Assigned members from the organizing committee will be managing the chat box and the website functionally. To begin with, the welcome speech will be delivered by Mr. Ushan Sakuntha, the president of the SEDS chapter of Sri Lanka Technological Campus. Over to you, Ushanaya.
Thank you, Hiruni. Very good evening, everyone. As the president of SEDS chapter of SLTC, I would hold a great honor in welcoming you all the webinar Nano Satellite Designing. First and foremost, Mr. Tharindu Dayarathna and Mr. Kaveendra Sampath, very warm welcome. Next, I would like to welcome Dr. Nanda, who is the advisor of SEDS SLTC. And we have Mr. Tina Shivani, Assistant Manager of Magnetar Division of SEDS SL Sri Lanka, joining here with us today. And it is a pleasure to hear you. I welcome Mr. Shivani as well. Last but not least, my heartfelt welcome to each and everyone who is present here to gain knowledge and to make this webinar a success. Welcome everyone. Thank you. Over to you.
Thank you very much, Shanaya. Moving on, now it's time for the most awaited segment of this webinar, the guest talks hosted by our two guest speakers. Let me take a moment to give a brief introduction about the guest speakers for today's webinar. First of all, Mr. Kaveendra Sampath. Mr. Kaveendra Sampath is an electrical and electronics engineer at the Arthur C. Clarke Institute for Modern Technologies, Sri Lanka, and a former assistant engineer at Lanka Bell. He received his bachelor's degree in electronic and communication engineering from the Open University of Sri Lanka and his master's degree, postgraduate diploma in electrical and automation from the University of Moratuwa, Sri Lanka. He has been working as a ground station manager at ACCIMT. He was also a member of the Ravana 1 Nano Satellite Development Team. Next, I would like to introduce Mr. Tharindu Dayarathna. Mr. Tharindu Dayarathna is an electrical and electronics engineer at the Arthur C. Clarke Institute for Modern Technologies, Sri Lanka. He was a former demonstrator at the Faculty of Engineering at the University of Peradeniya. He received his bachelor's degree from the Kyushu Institute of Technology, Japan, and had studied electrical and electronics engineering at the University of Peradeniya, Sri Lanka. In 2017, he had been assigned to the communication subsystem of the BIRDS project. Besides the communication subsystem, he was also assigned as a secondary person for the antenna deployment system. In addition to these marvelous achievements, he was also a member for the data collection mission, which was one of the main missions of the BIRDS-3 project. He was also involved in the Ravana-1 nano satellite project as an operator. The Ravana-1 satellite is regarded as the Sri Lanka's first nano satellite, built in the year 2019 and designed in Japan. Therefore, with immense pride and honor, I cordially invite both of our guest speakers, Mr. Kaveendra Sampath and Mr. Tharindu Dayarathna, to address the gathering. Over to the both of you, sirs.
This is the introduction to Nano Satellite Design and Ravana-1 Satellite Project. My name is Tharindu Dayarathna, Research Engineer, RTC Clark Institute for Modern Technology, Motor. So I did my MSc in Space System Engineering, Kyushu Institute of Technology, Japan. And I did BSc in Electrical and Electronic Engineering in University of Fairadenia. So I'll directly go to the presentation. So first of all, let's see what is a nano satellite. The term nano satellite usually applied to the name of artificial satellite with mass between 1 kilogram to 10 kilogram. If the satellite is 1 kilogram, 10 kilogram, we call this a nano satellite. Nano satellite can have various shapes, but it's standard to cube satellite unit. So you can see different shape, but it's easier if it is standard to CubeSat. So one kind of CubeSat unit is a cube shaped with 10 centimeter and 10 centimeter with mass somewhere between 1 kilogram to 1.3 kilograms. So I think Ravana-1 had about 1.15 kilograms. So it is in between this mass range. So there are you can see the different shapes of the cube satellite. It can be multiplied into different sizes: 1.5 unit and 2 unit and 6 units and 12 unit, 27 U. Some people say 27 U is not a CubeSat, but it still is a CubeSat, not a nano satellite, because it normally goes more than 10 kilogram. But sometimes people say it's as nano satellite. Even though we say one unit is 10 centimeter, 10 centimeter, and 10 centimeter, is one side little bit bigger. So it's around 11.33 centimeter. You can see in the Ravana-1 satellite. You can see one, it's little taller because that rail has a little bit more than the 10 centimeter. It's 11.35 centimeter. Now, you can see here there are many shapes in many cube shapes, so you can have different shape like this. So there are some example. This is some example of cube satellite. This is Ravana-1 and Ugisu. It's the same burst 3 satellite, and this is Nepalisat. They all flew together in space. And this is another one new satellite. This is a 2U satellite. It's called as Spartium. And this is a little complicated one. Recently, I worked in this one. It's a 6U satellite. You can see it's little bigger and it's a little bit complicated satellite. Actually, it has 2 satellites inside, which is Spartium and Kitsune. So actually, this is not Spartium. It's the continuation of the Spartium. One is actually Spartium 2 satellite is also inside this satellite. Actually, I work in those satellites. This is actually all the satellite. I have not seen this one before. I went to Japan. It was orbited. So it's a 27 new satellite. So if we talk about the nano satellite design, actually there are reviews introduced by US government. This is the reviews used by actually NASA also. There are many reviews called mission concept reviews and so many. And we actually, when we do the nano satellite also, we get some, this is actually this is the one we look, and we also use same system like this for our design. And this is what we use in our nano satellite, our round one design. We did a mission definition review, and we did preliminary design review, and critical design review, and flight readiness review. So I'll go through each one and tell you what are those. And actually, mission definition review, this is the definition I got from the Wikipedia. Actually, this is the correct definition, but I'll tell what we did in the mission definition review. Actually, this is where we define what we are going to do in the satellite as a mission. As an example, satellite, in our satellite, we had the camera. We say, this is where we define requirement and those mission details. We will not make a satellite at here. We just say requirement and what we are going to do. As an example, we will take a photo of Sri Lanka with 680 by 420 pixel dash size, and we'll send that photo to the ground every day. Like that, we define requirement and those objective here. And the preliminary design review, what we do here is we actually do a small PCB and those breadboard models. Like as example for the camera, we actually get a camera module and microcontroller and check whether we can do this one or not in a breadboard, and we show what we can do and those things in this design review. And then we go to the critical design review. Here we make a satellite called engineering model. Actually, in this engineering model, we have a satellite. It's similar to flight model, but it's not exactly like the flight model. It's not the finalized version. So we do the testing and those software testing, those many things with this satellite, and present here to improve in the flight model. So then flight readiness review. Actually, this is after we making the flight model of the satellite. After we do all the testing and all the software and functional testing, we do this review. So if this is fast, we can go for the launch. So I think I'll go through the Ravana one steps. You will understand what I said before, this CDR, FDR, those stuff. So introduction. Before I introduce about the Ravana one, I need to introduce about this project called BERS. It's introduced by Kyushu Institute of Technology, Japan. It's an acronym for the Joint Global Multi-Nation BERS Satellite Project. This project target non-space faring countries. Like it was, Sri Lanka was like that before Ravana. There was no satellite in Sri Lanka, so they target those kind of countries, and they call us and to join. And it's another target is build, test, launch and operate one new CHIP satellite within a 1 or 2 year framework. And all members were graduate students. So before the BERS, our project was BERS 3 project, and there was 2 projects before that. It's called BERS 1 and BERS 2. So this is the BERS 1 and BERS 2. In BERS 1 project, there were 5 satellites, and those satellites belongs to Japan, Ghana, Mongolia, Bangladesh, and Nigeria. And Mongolia and Bangladesh, Ghana, Mongolia, and Bangladesh, that satellite were their first satellite. And in BERS 2 project, there were 3 satellites. Those belongs to Japan, Bhutan, and Philippines. Actually, the Malaysia and Philippines. So in Bhutan case, that was their first satellite. And before talking about now, I need to introduce about the BERS 1 project members and the aim of this project. Actually, this project was introduced by Arthur C. Clarke Institute for Modern Technologies in technology collaboration with the Kyushu Institute of Technology, Japan as the first phase of the ACCIMT program for acquisition and development of the Sri Lanka national capacity in space technology. This was our ACCIMT aim, and you can see here, this is our Director General Sanath Panarangana. He was the one who introduced this project, and he introduced the concept of this project, and he named this satellite also. And he's the mastermind behind this project actually. Without him, I don't think there will be around one project. And next, Engineer Kamane Idrivir and Kaveendra Sampath, our director and the deputy director, they were responsible for management of the project on behalf of ACCIMT. And then me and Dulani, we were the engineers of the satellite site testing and development. And Kaveendra Sampath, engineer Kaveendra Sampath, he will present later. So he was the ground station designer and the development. It was under him. And then I'll introduce about bus 3 satellite. So we had 3 satellites called Uguisu, Ravana, and Nepali Sat-1. And this Uguisu belongs to Uguisu Institute of Technology Japan, and Ravana one belongs to Arthur C. Clarke Institute for Modern Technology Sri Lanka. And then Nepali Sat, it belongs to Nepal Academy of Science and Technology, Nepal. And this is the bus and bus 3 mission statement. Overall mission statement was make the first step towards creating an indigenous space program by designing, building, testing, launching, and operating the first satellite for participating nation. And bus 3 mission statement was build Sri Lanka's and Nepal's first satellite while improving the standardized bus system for future mission and give continuity to previous mission from bus 1 and 2. So I hope you understand what I said. And this was the project timeline. You can see here. We started this project October 2017. So it was a small meeting, and we started the project, and we had the MDR. I explained 28 December 2017. And we had a PDR. I said in PDR, we make a kind of like, it's not like real satellite. We make some subsystem. So we did that one. And then we had the CDR. At CDR, we had a satellite. So you can see the satellite without the outer panels. We did that one in 1st of September 2018. And then we finished the applied model January 2019. And then we delivered it to JAXA February 18th, 2019. You can see it's about from the beginning to the end delivery. So we use only about 15 months, 1 year, 3 months. And then in 1 year, 3 months, we make the satellite and finish it. And in 17th June 2019, we launched using Antaris rocket, and it was deployed in 17th June 2019. Now we are in the operation of the satellite. So you can see one photo we downloaded using the satellite. And let's go for the system design. And we have in a satellite design, we have something called product breakdown structure. We can divide satellite into 2 parts, ground section, main 2 parts, ground section and the satellite. Then satellite is divided into bus system and mission system. If you think about the bus system, we have a little bit. We have in buses system, we have a structure, OBC, EPS, and communication subsystem. If you think about this 4 parts, every satellite has these parts. So every satellite should have a structure of onboard computer and the electrical power system and communication subsystem. So every satellite has this have this part, and this is the part it changes. So the mission part, it depends on the satellite what they are going to do. This part can change. So in our satellite, we had camera, LoRa demonstration mission, and backplane board mission, and attitude determination and control system. And there was something called glue mission, but we did not have this glue mission in the FM model. So this is our satellite. So we use CubeSat standard. Dimension was 1 U, and you can see again it's around little bit, one side little bit bigger, and weight is 1.05 kilogram, and we use backplane type. So actually every board plugs into this board and it goes through this board, but there was a different backplane in the Japan satellite. So actually what happened is, let's say this board should connect to this board using wires on the board. It's hardwired. If we make a mistake, we cannot change those connections. So what we did here is we routed all lines to this chip, and we can route that line inside the chip using the software. So we can, using this software chip, we can change the connection. So actually it was a mission to check whether this chip can survive in the space. So because this is little bit risk, we put this board only in the Japan satellite, because we had not tested this chip before the launch. And this is the overview of the bus Cube satellite. And you can see we had the first board is we call a FAB board, front access board, and electrical power system 1 was in the first board. And then we had the battery box, and then we had the onboard computer and the electrical power system second part, and we had the communication board, then LoRa demonstration mission board, and then we had the camera board and the attitude determination and control system board, and the rear access board, and the antenna panel. So we take each board and plug in this backplane. So this is how it will look like. So when we plug into the backplane board, these are the outer panels. So this is the hardware we use for the satellite bus. This section is the bus 2. I'll explain about the bus 3. This is the Ravana 1 bus system part. So we use this PIC ICs for the onboard computer as the onboard computer MCUs. Someone can ask why you use PIC ICs, because those are very simple ICs, but in space, PIC IC will not have any problem due to those plasma environment in space. Actually, in the space, we have some protons and atomic oxygen. Those things can damage the complicated ICs, but this chips has history to survive in the space. So that is because of that we use these chips. So then the electrical power system, we use NLOOP nickel metal hydride batteries. And this is the battery charger chip. And I think it's just a chip. I will not explain about this one. And we had 3.3 volt power, 2 power lines. Then we had 5 volt power line. And then unregulated, 2 unregulated power line. Unregulated means power lines directly come from the battery without doing anything. And solar cell, we use these things, and it was not changed. And harness, we used software defined and normal hardwired. And the communication was 4,800 BPS. And this is, I said in the PDR, CDI state, we make a engineering model. This was the first engineering model. And in that engineering model, we had monopole antenna, but later I found this monopole antenna is not working properly. So then I had to change the entire satellite to entire satellite phase to like this. So you can see I changed this monopole into a dipole antenna, but the problem is we cannot keep the satellite like first photo if because of antenna hitting the table. So I keep like this, but this is not the proper way of keeping the satellite. Just to take a photo, I kept like that. And these are the flight model. So we had the Ravana 1 and Nepali 1 satellite and Uguisuk. And these are the team, the Sri Lankan, Japan, Nepal and Japan team. And you can see the Ravana 1 flight model. You can see the antenna is wrapped around these screws. When this coil get hit, this string burn and antenna get released like this. So you can see the antenna is like this, release. So operation concept. So actually we put this satellite into ISS orbit. It is around 400 kilometers above the surface of Earth, and inclination is about 51.6 degrees. And orbital period was 92.6 minutes. And we use amateur frequency band. Uplink was 135.313 megahertz, and downlink was this one, and this was the data speed. And then we had a ground station network. This will be explained by engineer Tharindu Sampath, and our bus system. So first we had the onboard computer. And you can see the onboard computer part in this white dotted box. So the major task of this OBC is collect sensor and each mission data and generate housekeeping data and store to the flash memory. And then second task is execute the telecommands from ground station and handle telemetry data and check satellite power condition and select operation mode was third task. And you can see the onboard computer block diagram. This is the main processor, and there are two processors other than that one to share the tasks in between those. So actually this is the UHF transfer. If a command comes, it goes to the communication peak and then transferred into main peak, and then those missions are executed. So I will not go through everything in this one. Then this is the next one is electrical power system. You can see that this is electrical power system board 1, and this one has those deployment switches, those battery chargers, and so many stuff here. And the buck boost converters are here in the onboard computer board. And objective of the EPS are provide uninterrupted power to the onboard electronics of the cube satellite in both sunlight and the eclipse. So eclipse means nighttime. In this ISS orbit, the nighttime is about 30 minutes per 90 minute orbit. So then control charging and discharging of the batteries and monitor current consumption of the loads and send those data to onboard computer. And protect CubeSat in case of fault situation, overcurrent protection. Like if there is overcurrent detection, overcurrent detection, it will be turned off by this electrical power system. And then ensure satellite preservation at the end of life. And this is the EPS block diagram. We have solar panel, and then power goes to 5 block-in diodes, and there are switches to isolate the this solar panel, and then goes to the battery charger unit, and this is the battery. This is the battery. So power comes from solar panels to the battery to charge, and sometimes if there are more powers, it will go to this side, or if not enough power, battery will supply the power to the system. So there are some switch to turn off the satellite. If we cut this switch, we can turn off the satellite, because satellite side is this one. So we had, I said previously we had unregulated power, which means direct power comes from the battery. So you can see the first one and the second one, and then there is a buck boost converter 5 volt, and there's a buck boost converter 3.3, and another 3.3, and another 3.3. And these are those switches. I said here there are switches. So these switches, you can see there here and here. If you remove these white things, satellite turn on. And this is the power distribution diagram. This is in the satellite side. So raw power comes from the battery. It goes to the 3.3 buck boost converter, and it powers those MCUs, and there are power buses. So you can see about 3.3 power line goes to the different section. I'll not go through this diagram later. Okay, so this was the battery box. So actually I made all the 3 battery box for the old satellites. So you can see we use Panasonic and loop nickel metal hybrid batteries. So we enclosed that one in a aluminum box, and there are some plastic things, and there are also heater inside to heat the batteries if the temperature goes below than 5 degrees Celsius. And this is the communication subsystem. This was my subsystem, and this is actually, it had 3 communication link. First communication link is telemetry and mission data downlink. It was frequency was 437.375 megahertz and bandwidth 26 kilohertz. We use GMSK modulation. We transmit 800 milliwatt from the satellite, and data rate was 4,800 bps. It was very slow, but to have a proper communication between ground station and the satellite, we have to have lower data rate, and we use this 435.313 megahertz for the uplink, and we use the GMSK and same data rate. And there was a CW beacon, and I think maybe you guys are not familiar with CW beacons. It's very old technique, but it is used to find where is the satellite and to get some data from the satellite. We use the same frequency as the first one, and it's about 500 hertz bandwidth, and we use CW Morse code, and the power was transmission power from the satellite was 100 milliwatt only, and we use 20 watts per minute. And this is the communication subsystem block diagram. This is the simplified one. I removed the other MCUs and connection from the OBC part. So transceiver board connect to the communication PIC. This communication PIC control every function in this transceiver. So you can see it's connected through UART. There are some digital lines going here and there. And this is the link budget. I think maybe if you talk about any communication link, link budget is very important. If we want to have a proper communication, we need to have this link margin greater than 0. So we had a positive link margin, and we could communicate with the satellite even in 0 degree elevation. So even though I calculated like this, but in the real result, I found out about 5 dB higher than this value, and we had a very good communication with the satellite. And this is the antenna subsystem. You can see the front panel, and antenna is wrapped around this screws. You can see there is we use actually fishing string for this one. It's stronger and it's plastic. We can burn it using a heat. So when this coil get heated, this one burn, and antenna goes like this and like this. So this is the back side of the antenna. It was actually very hard to find this component. I spent about 2 nights to find this one, this correct component. I did the calculation, but I could not find this component easily. So, but somehow I found later. And this is the deployed antenna. You can see the antenna like this. So actually we had two different frequencies in the uplink and downlink. So we got the average for the design. You can see it's exactly matched there. So if you are familiar with the S parameters, you will understand what is this plot means. Normally, if for a good antenna, it says less than minus 10 dB, S11 value should be less than minus 10 dB, but it had a very good minus 20 dB. So antenna worked perfectly. This is all three satellite. So here 87 means Nepal satellite. This is Japan satellite. This is Ravana one. You can see all of those behave exactly similar. So I went back. So this is the anechoic chamber test we perform to measure the antenna radiation pattern. You can see the anechoic chamber. This is the reference antenna. Then we have a satellite. And this table rotates to get the reading. And this is the radiation pattern I measured. So if you are familiar with the what is called dipole antenna radiation pattern, in the H plane it has something like this, and E plane is like a dumbbell shape. You can see it's close, is similar to those shapes. And testing in satellite, this is a very important part. If you don't design if we don't do the test properly, satellite will not be accepted from JAXA or the space, any space agency. So this is the long range communication test we performed. You can see me just sitting there and do the test. So what we did was we took the satellite to a very tall mountain in Kyushu. So actually this place was very good to do the test, because if you keep the satellite on this this thing, actually this is a very famous place. People come to take photo with this cockroach. So but we use that one to do our test. So if I look through this hole, I can see the ground station, our university, about 6 kilometers away. Say, actually a very good place to have a proper line of sight communication. In this test, actually there was we did about 4 tests. This was in the winter. It was about -1 degree Celsius. It was very hard to do the test. And then we used anechoic chamber to tune and those things related to antenna measurement. And then thermal vacuum test. Actually, purpose of the thermal vacuum test is measuring temperature at different points under extreme hot and cold condition, and check functionality and operation of the satellite. Check antenna deployment mechanism under worse cold condition. Actually, what we do is we cool the satellite and check whether antenna deploy at that moment also. If it deploy at that moment, higher temperature, it will definitely get deployed. And check operation of the battery heat and thermal monitor under defined temperature ranges. So, and then this is where we prepare the satellite before the thermal vacuum check test. We put a lot of thermocouple inside the satellite and get the wires outside, and it's very hard to get wires outside because there are many thermocouples. There are no holes to get it outside, but we manage somehow. And this is the thermal vacuum chamber. You can see satellite is inside. To heat the satellite, we use this heat coil, and to cool the entire surface of the satellite, we pump liquid nitrogen and cool the outside of the chamber, and then it get cooled. And after closing this chamber, it become a vacuum. We have to pump out the air inside the chamber. And this is the profile we use for the testing. So you can see these are the plot of the thermocouple readings. So you can see all thermocouple goes around -45 degrees Celsius and goes maximum 6 Celsius. And we perform a function in the satellite in these critical phases. Like as an example, you can see we deploy the antenna here. There's a sudden temperature increase because of that heater coil turn on. So you can see that jump also.
and every function is function up upon this maximum temperature and the minimum temperature. And if everything okay, we say this test okay. And then the vibration test. This is one of important test. The purpose is to evaluate the impact of vibration by launch vehicle on the satellite. Actually, when rocket is launched, there are very high vibration. It can damage the satellite. So because of that, we need to check whether the satellite can survive in that condition. So success criteria of vibration test are no significant shift in natural frequency, no shift in torque marks, which means if we put a screw, we mark a torque mark, and if it is changed, it means the screw is rotated. So no fracture or critical parts, including glass components. Glass component means solar panel. So we need to check whether solar panels cracked or not. If it is cracked, it cannot generate power. So then antenna shall not deploy during this test. So I think you guys understand what I mean. Satellite shall remain off state. So satellite should be in off state, which means satellite cannot turn on while launching using a rocket. Satellite should function before and after the test. So what we do is we check the satellite before putting into the vibration test, and we check the satellite after putting the vibration test. So then we can compare the performance has changed or not. And this is the test setup. We have something like this. It's actually it's a kind of like a very big speaker. So we check for the each axis. So actually we do this. We vibrate this satellite using 13G acceleration. 13G means it's like 13 times gravity of the acceleration due to gravity of the Earth. So it's so very high vibration. Sometimes fly away from the satellite. It's very high. And these are the test flow. We do functional test first, and then prepare and do some model vibration test, then the random qualification test, and then the model vibration. Then we do a assigned burst. I think I'll not go through these things more, so because it's a little bit complicated. The report was about 500 pages for this test. And these are the plot we got from that test. So you can see the frequency and the power spectral density values in the different accelerometers. And this is y-axis sine burst test. And then I'll explain about the missions. We had the camera mission. Mission statement was take first step for the future remote sensing application. And mission objective was take images for media in RGB, red, green, blue, and raise awareness about the existence of the satellite. So we can say satellite is there, and satellite took a photo. What that means in a second. And the launch outreach activities in a school, we can give to schools and to do those remaking photos. And this is the camera hardware. This is actually EM board. You can see a resistor. Actually, it was not there. This is just for testing. We put a resistor. So this is actually EM model. This was not the flight model. And you can see we use a 5 megapixel camera. And the ADCS mission. This is actually attitude determination and control system. Mission statement is take first step towards pointing for the future remote sensing application. Actually, mission objective was stabilize the satellite and qualify onboard sensor for space. Actually, what this mission do is initially when satellite get deployed, it has some rotation. It control this rotation of the satellite using this mission. And this is the hardware part. It was ADCS part was also in the camera board. You can see this section is the ADCS part related stuff. So you can see a gyroscope and microcontroller, magnetometer, and GPS and MTQ. This is actually the using this MTQ magnetic torques. We create an anti-magnetic torque with the Earth magnetic field and get a rotation using that one. So we had three perpendicular. We had these magnetic torques in three perpendicular surfaces. This is one of that. And LoRa demonstration mission. So take first step towards the low powered communication system for satellite. Space qualify LoRa module, however, not emit RF. So what happened was we want to communicate with the satellite and the ground station using LoRa technique, but we did not get any license. Because of that, we just wanted to qualify that chip work in the space condition in the plasma environment. So we use that mission. It just communicate inside the satellite. So if these two chips can survive in space for the entire lifetime, we said chips can be used in the future mission. So actually we use this one in that previously mentioned ACCIMT satellite, because in burst 3 it worked perfectly. And the backplane mission, I explained that. I explained this one before. Instead, I standardized the communitized the possibility backplane board for future mission. So will I go this one? So here I'll explain it again. If you get these connectors, you can see lines are hardly wired. So if we make a mistake in this connection, we cannot change it in the hardwired board. So, but using this chip, so what we can do is these lines are routed to this chip. Inside the chip, we can change the line to any pins we want. So then engineer Sampath, Kaveendra Sampath will take over presentation from here.
Okay. Thank you, Tharindu. I think hear you. Excuse me. Can you hear me?
Yes, sir, you're audible. Yes, sir, you're
Yes,
audible.
Sir. Okay. Thank you, Mr. Tharindu Dayarathna, and let me go into about the ground station operation. Actually, ground station operation, there's two parts. What is the ground station and why we want to ground station? When we consider about the ground station, actually there are some two segments. Now Tharindu explained the space segment, totally about the space segment. There's another segment called ground segment. This ground segment is mainly used for the communicate with the satellite. So ground station means transmitting and receiving, and receiving things to the satellite. And also there's a two station also. First thing is the ground station, and other is a satellite station called space station. Those are the two stations. Next slide. Yes, next one. Next one. Okay, thank you. Why ACCIMT want to ground station? Actually, first we consider about the Ravana 1 satellite and BIRDS 3 other satellites, Ugusu and Nepal satellite. We have to have communicate with them so that we introduce the Ravana ground station, and also there's another method, another satellites called NOAA, National Oceanic and Atmospheric Administration. There's some foundation, they launched some satellite for the weather forecasting. So we can get some information from that NOAA satellite also, and communicate with other amateur radio frequency operated satellites. In example, OU4 in Tharindu's presentation beginning side, there's a Horyu satellite. Horyu 4 is already operating that one, and also Suru is a new Birds 4 satellite. We can communicate with these satellites using our ground station. Next slide. Okay. Actually, this is the CW beacon format. CW means continuous wave. This is the very basic communication method and very attractive communication method, because CW communication method, there's a long big history there. I think Second World War also used this method, CW method, and after that ships communicate with these CW methods, and airplanes communicate with CW. And after that, when increasing and developing the communication systems, CW communication system got decayed. And I think in this session, some amateur radio operators are there, so they know about the call sign. In this format, there's a call sign, satellite name, message, and housekeeping data. Call sign. Call sign mean in amateur radio, there's some person identification system, person or some object or some places. That means shack. We call shack. In example, in RTC Clark, we have some call sign 4S7 AC. This is the RTC Clark call sign, 4S7 AC. Some in amateur radio persons, there are some 4S7 ABC or something. There's a call sign. This call sign used for the identification the person or some shack. And why we want to call sign to the satellite? Actually, in Tharindu said we use amateur radio frequency band, and actually 437 something. 437 means this frequency band belongs to the amateur radio. If we select some frequency, if we choose some frequency, we have to have registered the ITU. ITU means International Telecommunication Union. Okay, and we have to pay this frequency allocations and so many things. And in Sri Lanka, we have a local authority called TRCSL, Transmission Regulation in Sri Lanka. So like this, the TRCSL directly connected with the ITU, International Telecommunication Union. When we use the amateur radio frequency, we have this is the research satellites. Actually, we have saved some more money, because when we get some particular frequency from ITU, it's a very big cost and very big process also. And so that we use amateur radio frequency, so that we have to have used the call sign. In our case, in Ravana, we registered in the Japanese amateur society. So we have JGY6LG. JGY6YLG is the Ravana 1 satellite call sign. And there's another call signs, JG6YLF and LE, Nepali and Japan satellites. Then satellites name, in here, Birds 3, this is the project name actually. Project name. There's a message. Next part. Message mean we can send some name or some organization name to transmit over the world. This is some actually this attractive thing for in amateur radios and amateur radio practices one. And final part is the housekeeping data. This frame is there's a fragmentation, battery voltage, battery current, battery temperature, and satellite sales. This battery voltage, battery current, battery temperatures, those values are this is the we call hexadecimal value. So we can convert this value to the numerical value, so that to do this work, the amateur radio, the Birds 3 satellite group, they developed some software. Next page, I think this is the software. This software, we actually, we have two types of CW. This one, there's some battery voltage, battery current, battery temperature, like this, and solar cells. Another one, gyro values. After the tail side 10 digits data, we can put into the CW code here, and satellite also, satellite name also, yeah. Then we can click the analysis. In example, in here CW1, there's a battery voltage 4.2, battery current -6, battery temperature 12.4. This is the housekeeping data, because this data is very, very important to us to get some information about health about the satellite, some health about the, how to work. And other than that, there's some solar cell shadow and shiny. There's some shadow and shiny. That means which side of the solar panels towards the sun, which side of the shadow part. So in that situation, we can get some idea about the power generation and orientation of the satellite. Okay, so this is very vital for our purposes. Next slide. This is the ground station operation software. Actually, we communicate with the satellite using amateur radio. That's mean 433 band radio, VHF, UHF radio. I will describe later. And that radio and TNC. TNC is the terminal node controller. That terminal node controller is the main main part, because it's a data decoding equipment. And the TNC and radio both are connected to and controlled using this software. Actually, this is the software totally control the satellite. If you want to control the satellite, you have to have this software. Okay, otherwise we can't control the satellite. Then next slide. Okay, this is the general architecture, general block diagram of the ground station. Okay, this upper side boxes, there's ANT1 2 meter, ANT2 70 meter. This is the antenna. 2 meter and 70 meter means normally we can say some frequencies in 470 megahertz or something, or otherwise we can tell that frequency in centimeter level. That means wavelength. In amateur radio, they most probably use that wavelength frequencies type. That means 70 centimeter mean UHF band, and 2 meter mean VHF band. In example, 140 megahertz, rounding 140 megahertz is 2 meter. Rounding 430 megahertz, 70 centimeter. So if amateur radio on, yes, these days I receiving for 70 centimeter. 70 centimeter mean UHF band. So then a coaxial protector. This is some surge arrestor. We can use a surge arrestor because protect from the surge, lightning, and also preamplifier there and transceiver. Then this antenna to the transceiver, we connected the coaxial cable called, it's commercially named RG8 50 ohm cable. There's some large varieties cables. It's specifically we have to select specification, the low attenuation cables we have to select, and then transceiver connected to the TNC, and transceiver and TNC connected to the PC. That PC is based on the ground station operation software and satellite tracking software also here. I'll describe later. And in our case, in Arthur C. Clarke ground station, actually we didn't use preamplifier part, because we just connected to antenna and transceiver, because actually our antenna system is nearly 32 years old. Then I think it's in ACCIMT document. It's purchased 1988, around in 1988. Now all the part we replace in local parts in antenna, and this antenna VSWR is 1.01. It's a very good one, and since this radio is very sensitive radio, so that actually we didn't want to preamplify part. So we didn't use this preamplifier. We just connected the transceiver. Then other part is the rotor part. That rotor part is used for the antenna tracking. That means track the satellite. When we consider about the satellite passing in Sri Lanka, overhead passing, we have to have direct the antenna towards the satellite. So that part done by using rotor. So next slide, Tharindu. Yeah, this is the technical specification about the transceiver and TNC. Transceiver is ICOM 9100. Actually, this is the very high sensitivity and very accurate transceiver. It's a very good one. And I think all the 15 ground station all around the world, there's a 15 countries gathered with the BIRDS project. So I think all are use this ICOM 9100 transceivers. And this is the TNC. I said you this use the actually in this transceiver we can't transmit the digital modulation. Actually FM, AM, CW we can transmit or receiving using this transceiver. But when we if we want to get some digital modulation, we have to use TNC. In TNC, there's a digital data transferring method called AX.25. Do you know? These days we use normally we use Ethernet. Technology is Ethernet. Okay, and above the Ethernet we use TCP/IP packet frames. Before that, there's some technologies. Ethernet also technology. There's a technology token ring, frame relay, and X.25. This X.25, after that, amateur radio, the persons they create as a AX.25, amateur X.25. This is the X.25 packet frame, and modulation. Tharindu said that there's some GMSK modulation, and frame is the X.25. And next slide, Tharindu. This is the satellite tracking equipment. Actually, the black unit is the azimuth and elevation controller. This is the actually is the actuator, and gray color box is a controller. It's a Kempro 5600B. This controller box is actually it's the analog one. So we have to have media converter to connect it to the computer. So GS232B is the some RS232 to connect to the this box. Actually, computer controller box. When we next slide, Tharindu. Actually, this is the SATPC32 satellite tracking software. This software is the prediction one, and we can detect the satellite point. And this SATPC32 gives azimuth and elevation data, and also rotor. This is the rotor controlling data, and also radio controlling data. That's mean you know the satellite frequency, so transmitting frequency 137, and its orbit speed is 7.62 kilometer per second. It's very big speed. So that in that time, that radio frequency can be shifted according to the Doppler theory. So that Doppler correction have done by using this SATPC32 software. This correction transmitted to the transceiver. Okay, sent to the transceiver. Then transceiver correct that data. And also, this is the other side, the right side. There's the antenna. A big one is the UHF one. The small one is the UHF one. This is the UHF one. Actually, in our case, we want a UHF antenna for satellite communication. And center part is the satellite actuator. I said you, the black part is the actuator, and cross boom here. The cross boom is the grip the two antennas. So this is the our antenna structure and tower also. And this antenna is a Mass Pro cross polarized Yagi antenna. Gain nearly 13 dBi and more than 18 elements there. Cross polarized. Okay, next slide. And again, there's some two softwares, PST rotor software and CW skimmer. Actually, PST rotor software, that software is intermediate software in between SATPC32 and controller. Actually, other countries, that means Japan or Bhutan or Nepal, they didn't use this software. Only Sri Lankan ground station, in our ground station, only use this software, PST rotor, because we use this one. Actually, you know, some wind situations, some rain situations, antenna have some drifting, and drifting along the main boom, cross boom. There are some slippering, and there are some changes in the antenna orientation. In that situation, we can error correction through this software. This is so that this is very vital. Actually, there's a routine maintenance method. Routine maintenance method. Once a month, every part we checked. Antenna leveling, antenna orientations, everything we check. In between, there's some small correction we can do using this software. Otherwise, every time we have to tighten the antenna parts. So we can eliminate the using this software for that part. And CW skimmer, in amateur radio operators, they decode the CW using their naked ear. So they can decode this CW beacon very quickly. In we call DIGDA methods. They decode. But this is the research project. We have to have evidence. We have to keep the evidence for the data. So that we have to use CW skimmer for recording the data, and that old recorded data we keep in the computer and files, because they all we want to the future purposes. So CW skimmer is the CW decoding software. Next slide. Yeah, this is the actually in-house developed software, just like a SATPC32. Actually, I am memorized Mr. Vignesh, who's a training in Arthur C. Clarke from OUSL. He done that work using JavaScript. Actually, we want to create some own platform in Sri Lanka. This is one step for this target. We developed that in-house development software. And next slide, Tharindu. This is the ACCIMT ground station establishment. Before the establishment, this is the appearance of our ground station. This is the actually not a ground station. This is the amateur radio operation center. We refurbish all the things, rotor part, side booms, antenna, everything. Then establish the new ground station. Next slide, Tharindu. Actually, this is our ground station establishment part. Mr. Kaveendra Sampath is a software engineer and good carpenter also. He's a software engineer, but he's some good talent guy. He's the best support for this establishing the ground station. And next slide, Tharindu. This is our ground station establishment time. Next one. Okay, next one. Okay, finally we achieved the target. This is our ground station. Okay, this is the ground station, the transceiver and all the TNCs and PCs there, and controlling system and controller. This is the controller. This is the right dotted. This is a controller and antenna controller and all the things here. Finally, we achieved our target, and we have get first place from the all the 15 ground station in birds 3, because we are the first successful transmit to the satellite in Sri Lankan ground station. It's the first place. Next slide, Tharindu. This is the historical moment. In 2019 June 2017, in evening 17:55 is the first receiving signal. The satellite actually this is the first time satellite put into the orbit, and after that we can get the CW. And in below, this is the first transmitting successful time. We take some images, and this is the reply from acknowledgement from the Ravana satellite. And next slide, Tharindu. And this is the birds ground station network all over the world. And red color one, birds one project, QTech University, and other Costa Rica, and there's some 15 ground station all over the world. Yes, next. Okay, this is the first image. Actually, left side one is the first image, I think, and second one is the down south of the Sri Lanka. These are very famous images from the Ravana 1 satellite, and the next one. This is the very good image among the I think nearly more than 30 photographs we have in all 3 satellites, more than 30 or 40 Ravana 1, Nepali and Ugusu satellites. We took more than 40 photographs. Among them, this is the very clear and very detailed full photograph. This is portrait. Here's a Jaffna Peninsula there, and down south of the south side of the India, and portrait is very clearly shown. So actually, this is the scientific satellite. Not only actually, so that this is, I think, a very good image for this type of satellite. Next one. And this is the also down south and Sri Lanka image. This is our achievement actually. This is our achievement. Then next slide. Thank you. This is our link for you can get some information about this project and satellite details. Thank you for kind cooperation with this presentation. Okay, I hand over this session to the admin.
Thank you very much, Mr. Kaveendra and Mr. Tharindu, for sharing your valuable knowledge and experiences with us. And thank you once again. Now, Ms. Tina Shivani, representing Magneta Division of SEDS Sri Lanka, will address the gathering to give a brief introduction about SEDS Sri Lanka. Over to you, Ms. Shivani.
Thank you, Hirani. I hope I'm audible.
Yes, you're audible.
Thank you. Students for the Exploration and Development of Space, SEDS is a non-profit organization that empowers young people to participate and make an impact in space exploration. SEDS helps students to develop their technical and leadership skills by providing opportunities to manage and participate in national and international projects, as well as to attend conferences, publish their work, and develop their professional network, and to become more effective in their present and future careers in industry, academia, government, and education. SEDS Sri Lanka is a leading organization that consists of students and young professionals to get experience in astronautics while disseminating new knowledge among the Sri Lankan community. Founded in September 2018 by Amila Sandun Basnayaka and Thilan Harshana, currently the main organization, SEDS Sri Lanka, governs 16 chapters established under it, hailing from 18 government and private universities, as well as a separate chapter for school children named SEDS Juniors. A wide range of activities are carried out throughout the year. SEDS Sri Lanka currently operates under 7 major divisions as Rocketry Division, Robotics and Rover Division, Observation Division, Satellite and IT Division, Biomedical and Earth Science Division, Financial Division, and Media Division. The organization has brought international glory to our motherland as a unique organization that is run entirely by students and young professional volunteers through projects such as Serendip 1.0, which was Sri Lanka's first scientific high-altitude balloon. We have a unique insight into the Sri Lankan space sector from a student's perspective, using our expertise and data to advocate for the development of the space skills pipeline. SEDS Sri Lanka is currently working on an underwater monitoring research project and a CubeSat development project. Through projects like these, the organization hopes to collect crucial data which can be utilized for the betterment of future science. Also, competitions such as NASA Space Apps Colombo 2021 and Act in Space 2021 will be carried out in the near future. Thank you.
Thank you very much, Ms. Tina Shivani, for that wonderful introduction about SEDS Sri Lanka. And next up, it will be the time for the live Q&A session. You could all simply just log into the website using the link in the chat box or by scanning the QR code displayed on the screen. In case you encounter any problems with the Wevox platform, please feel free to drop in a text onto the chat box. We will be choosing questions with the highest number of votes. Thank you very much for your curiosity and sending in so many questions. And I would like to say that these questions are open to both our guest speakers. The first question that one of our participants has asked is, what is the most effective and cheapest way to launch a satellite and keep it orbiting Earth for a long time, like most satellites? Sir, both of you can answer the question.
I think maybe the question little bit complicated, not complicated. Like I had to divide it into two parts. Like cheapest way is using as a research, like orbit as a research satellite using amateur frequency band, but and use the ISS to deploy the satellite, and that is the cheapest way. But the problem is if we deploy into the ISS orbit, that is it's not a good orbit. It will not, satellite will not remain at that orbit for long time. Maximum it will be about 2 years. If you want to keep the satellite in the orbit more time, you have to send it above the 500 kilometers. So for that one, you have to use a rocket, and you have to rent a rocket. That is very expensive. I think there is a contradiction with these two cases. So I think hope I answered the question.
Yes, sir. Thank you very much, sir. And also there's another question from one of our participants. What is the maximum and minimum temperature for this satellite for its working condition?
Okay, we tested condition is from minus 45 Celsius to 60 Celsius, but the minimum temperature we recorded was in the outside panel was about minus 5 Celsius, and the maximum was 45 Celsius. But inside, it was minimum was about 10 degrees Celsius. So it did not go below than 10 degrees Celsius. So that was the answer. That is the answer.
Thank you very much, sir. And also another participant is asking, what if we use nano satellites for deep space exploration?
Okay, nano satellite for deep space exploration. So I think the problem is with the one new cube satellite, we cannot do a deep space exploration, because let's say you want to see some star or something, you need to have a better optical system. So which means that there should be some kind of like a telescope thing. So at least you have to go for a 3U satellite. In 3U satellite, you can do that one easily. Not easily, like it will be very complicated satellite, but still you can do it with the 3U or more than that one. Okay, that's the answer.
Thank you very much, sir. And another question. Advanced Communication Engineering is an elective module of BSc Engineering degree. Do we have to select it in order to go for the satellites area?
I think we both will answer that one. I'll first answer the question. So if you want to do a communication, do all the subject. Don't just reject the subject. Like me, I did all the subject. So at least you will get the idea, even though you don't understand everything. So it's better if you have just even gone to the lecture. No need to write the exam, but at least get the knowledge from those things. So if you registrant want to get credit, so do it. But I suggest you to do all the communication subjects if it is available. So yeah. So Sampath, I muted.
Yeah, sorry. Actually, you have to do the communication subjects and also electronics, both. And other things, if you want to study the satellite, you have to know about the orbital mechanics things, little bit about the orbital mechanics things. So in universities, they can able to put that orbital mechanics things. It's good, and I think electronic and communication, since if you can go through the harder, it's better.
Yeah, I'll add little more. So You don't need actually advanced communication for the cube satellite like Ravana one, but let's say you want to like improve the performance of Ravana one in a later satellite. You need to know everything. It's better doing all the subjects if it is available. Okay.
Thank you very much, sir. And there's another question. What are the power sources in a nano satellite? Can we use another power source without using solar power?
Okay, what kind of power source? Like, okay, let's say the solar power is the main one. So it is easy and not complicated, okay? But if you want to, like, let's say you go beyond Saturn or somewhere beyond our solar system, solar power is not available. So for that one, we need to use something like nuclear power. But in the near the sun, we don't need to go for those things. I think it's a kind of like it will make the satellite very complicated, and we will not be able to implement other systems because of that extra power source. Okay.
Yes, sir. Thank you very much, sir. And also there's another question. One of our participants is asking, is Ravana 1 satellite still active?
Yeah, it's still active. If you have a SDR and antenna, you can get the beacon. So yeah, and it will be going, I think it will be entering the Earth atmosphere in 7 or 6 months from now. So it's active and perfectly working. And I think Sampath can say about that one.
Yes, if you can use this SDR or some antenna to fine tune to the 437 frequency, you can get the CW beacon. Actually, these days we received this satellites data, but currently in I think in 1 week or 2 we stopped that because the corona pandemic situation. Otherwise satellites is okay. We downloaded some data and we get the CW beacon also, and according to the level of the satellite, I think now it's in about 370, around in 370. Is it
365?
65, yeah, 65, around in 365. So we think it's more than 6 months or 8 months, and fully covered our target, because normally cube satellites the age is 2 years. Now completed the 2 years in Ravana also. Next June 17th is achieved the second day. So it's working fine.
Thank you, sir. Actually, the same participant has asked 4 questions. So one is like, is the Ravana 1 satellite still active? And the second one is, what is the bandwidth and frequency on which it transmits? Can I go on saying the third and the fourth, or would you want me to like stop at the second one?
Okay, go ahead.
Okay, okay. How can I receive it? I have a ground station, signals, power, and other technical details. And he's also asking decoding and demodulation details of the signals. Actually, the same participant is asking all these 4 questions. So, sir, can you give like a brief explanation on all this?
Okay, I think presentation had the frequency at the bandwidth. So downlink frequency is 437.375 megahertz, and it's 26 kilohertz wide bandwidth. and you can decode the data using some softwares, but it's very little complicated to explain here. Maybe you can contact us later, but you cannot send any uplink to the satellite because it's prohibited to do by others. If something is there, Sampath, you can say something.
Yes, actually, it gets the answer. 437.375 is the frequency. If you have SDR, software-defined radio, and there's some freely available software in the internet. In example, SDR Sharp, you can get, but I think sensitivity is not enough. Sometimes some sensitivity is not enough for the SDR. And if you have a good antenna, tuned antenna, you can get that signal. Actually, in Sri Lanka, amateur radio operators, some operators, they pick that signal using their handheld sets and SDR also. They get that signal very easily.
Yeah, we can guide him to
Yes.
decode the data if he want.
Yeah,
Need to contact later.
Definitely.
Thank you very much, sir. And also there's a question from SEDS SL, especially. If designing a cube satellite in Sri Lanka, is there any place with facilities to do these testings in our country?
It's direct no. We don't have the, actually we can test like communication, we can do communication tests like communication tests, but we cannot do thermal vacuum tests, vibration, those things are not available in Sri Lanka.
We have the knowledge.
Yeah, we have the knowledge, all the knowledge, but facilities are not there.
Facilities and thermal vacuum and vibration, also vibration and thermal vacuum. And if we use the ADCS, there's some chamber. That means ADCS checking chamber and Anechoic chamber also for the antenna checking. So
actually, actually what we can do is we can make the satellite like Ravana one using Chinese companies, those PCBs, and assemble the satellite. But we have to take the satellite to, as example, QTech, my university in Japan. So we have to take it there to test that, because all space agencies has what is the standards. So you cannot do just test. So we have to do at the correct place to those tests.
Thank you very much, sir. And also another participant is asking, what steps can you experts, including Arthur C. Clarke Institute, take to develop the astronomical sector in Sri Lanka?
I think Kaveendra, yeah, should answer that one.
Excuse me, sorry. Repeat that question.
Yes, I will repeat it again. What steps can you experts, including Arthur C. Clarke Institute, take to develop the astronomical sector in Sri Lanka?
Actually, there's some steps take place, and in example, in astronomy side, this actually Tharindu and me, we are in space application, not astronomy side. Astronomy is another side. There are some directors and some guiding peoples there. So actually they did some good things to the astronomy side in up to now. Actually, in detail wise, I can't tell anything astronomy side, because Tharindu and me, we are space application side.
We are space system.
The problem.
Based. Yeah. We actually you have to contact those person in charge in ACCIMT to.
Yeah.
Okay.
Yes, sir. Thank you very much. And also there's a question from another participant, and it's in Sinhala. ශ්‍රී ලංකාවේ අනාගතයේදී තවත් නැනෝ සැටලයිට් දියක් කිරීමට නියමිතද? That's a question, sir.
මම කියන්න නේද answer එකට.
තරුණ කියන්න.
මෙහෙමයි. එක සැටලයිට් එකක් හදලා ඉවරයි දැනට. ඒක කිස්සුනේ කියලා මම කලින් පෙන්නමු සැටලයිට් එක. ඒක ආර්තර්සි ක්ලාක් ඉන්ස්ටිටියුට් එකයි කියුටෙක් එකයි තව නැන්යන් යුනිවර්සිටි එක සිංගප්පූර් එකයි ඒ ගාවට ජපානි කම්පැනි දෙකක් ඉන්වෝල්ව් වෙලා හදලා තියෙන සැටලයිට් එක. කියන්නේ අපේ පාර්ට් එකකුත් ඒ සැටලයිට් එකේ තියෙනවා බොහෝ දුරට ඒක මේ දෙසැම්බර් වගේ ලොන්ච් කරා. ඒක 6U සැටලයිට් එක 6 ගුණයක් ලොකු විරාවනා වගේ. ගොඩක් කොම්ප්ලිකේටඩ් සැටලයිට් එක. ඉස්සරහට ඒකෙන් පස්සේ ආයසර රාවනා 2 වලටත් අපි බොහෝ දුරට යන්න ඉඩ තියෙනවා.
දැනට ඒක සම්බන්ධව යම් යම් දේවල් සිදු කරමින් පවතිනවා. රාවනා 2 එකට යන්න ඉඩ තියෙනවා.
ප්‍රශ්නේ තියෙන්නේ මෙතන අපිට දැන් සැටලයිට් ප්‍රොජෙක්ට් එකක් කියන්නේ මේ තැන් වලින් නම් කරන්න පුළුවන් වැඩක් නෙවෙයි. කතා කරලා කරන්න ළඟ ඉඳන් කරනවා පොඩ්ඩක් අර work from home හින්දා ටිකක් slow වෙලා තියෙන ප්‍රොජෙක්ට් එක.
අනිත් එක ගොඩක් ඒකට ඉන්වෝල්ව් වෙන්න ඕනේ. ඒකේ ගොඩක් මේක සම්බන්ධ ඒක තුල ඉන්න ඕනේ. ප්‍රොජෙක්ට් එක තුලම ඉන්න ඕනේ. එතකොට මේ වගේ සිටුේෂන් එකක මේක අපිට විතරක් නෙමෙයි මේක ජපානයේ තරුණ පිරිසලා මේ අධ්‍යයනය තියෙනවා ජපානයේ කියුටෙක් එකේ මේ පැන්ඩමික් සිටුේෂන් එක නිසා. මේක හැමතැනම ඉතින් බලපාන දෙයක්.
ඔව් අපි හැබැයි හිදී අර වෙන බබල් එකක් හදලා තමයි කරේ කොහොමද?
වැඩ කරා. ඒක තමයි බබල්.
හරිනේ.
Yes, sir. Thank you very much, sir. And there's another question. Can you also please explain how the dipole antenna is unfurled by the string? Is it burnt by a controlled electrical component, or is it due to conditions in outer space?
Like outer space cannot burn it because it's about 40 degrees Celsius. So there's a coil. So we send about 2.5 ampere in about 15 seconds. It will get red hot and burn that one. So that is how it happens. It will maybe it goes around 600-700 Celsius in the coil.
Yeah.
Okay.
Thank you very much, sir. And also another participant is asking, how is satellite protected against debris?
Okay. I think it's kind of like the probability is very low to hitting with any other debris. So this is very small. Even the ISS, it does not get any debris like for a long time. It's like very low probabilities. You don't need to worry about the debris. There's no protection. If somehow it hit, satellite will be vaporized.
Vaporized. Yes.
There will be no protection.
Because in satellite, in deorbiting situation, it's collide with the oxygen and normal atmosphere. It's got burned. Yeah.
You don't need to worry about any debris. So
yeah,
it
yeah.
will not.
No, it's
only thing is you will hit with a bigger satellite, but the thing is there are no more satellite below 400 kilometers, so you don't need to worry. And ISS is about 400. Yeah. Okay.
Thank you very much, sir. And also one of the most requested questions in this webinar is what about Ravana 2? So everyone is like really excited about it. And the question is, what about Ravana 2?
Ravana 2, actually we are doing the initial design right now. We have finished we have finished 3 boards design. So we finished the bus system. Actually the design is finished. We need to fabricate that one. And we need to put mission system. We will make an engineering model. So, but we are not sure how we launch this one. So we need to think about that one later, maybe in 2 or 3 years situation.
Thank you very much.
It's not official. So what we do is we just preparing and be ready with the satellite for the Ravana 2. Okay.
Well, thank you very much, sir. That will be all the questions for the Q&A session. And thank you very much for your experiences and the knowledge you shared with us. And thank you very much once again. So I think today was such a memorable day. I personally actually learned so many new things on nano satellites and its design. And a huge thank you goes out to the both of our guest speakers for taking time out of their busy schedules and gracing us with their presence here today. And also, we have a small announcement for all our space enthusiasts. SEDS in collaboration with the Nepal Orion Space and IEEE MTTS has organized a lecture series and a workshop starting from the 15th of May 2021 about cube satellites and their communications. The duration of this lecture series will be about 1 month, and the workshop will be conducted in the physical mode once the prevailing COVID-19 pandemic situation in the country is under control. Thank you.